Okay, I'm going to talk about energy right now. So here is a copy of the formula sheet for the AP test, and I'm going to just highlight a couple of things here that are related to potential energy. Okay, so the things I want to show, not just potential energy, but energy in general. Okay, some important things. First of all, power is the rate of energy use, so energy per time. Instantaneous power can be found by multiplying the force times velocity. And formula for kinetic energy, formula for gravitational potential energy, formula for elastic potential energy or energy in a spring. Okay, this formula right here represents the strength of a spring, depending on so how much force a spring exerts based on its stretch. And actually, so this highlights a really important thing. So this equation here comes from taking the integral of that. So the negative integral of f with respect to x, and this is, let's make this general. So potential energy is equal to the negative integral of f with respect to x. This is true of energy, okay? That's how you get the spring formula from this spring force formula, okay? And this is basically a restatement of this equation right here, because work is equal to a negative change in potential energy. Okay, now just let's take a step back here, and I just want to say that I really dislike talking about energy in this way because I think it's pretty confusing, and work is just a really tricky thing to talk about. It's very difficult to talk about work in a way that makes sense and to do it correctly, okay? So it's okay if you're confused, but the key I want you to understand is that this and this are kind of two of the same equation, and this relationship here is important and something that you need to know. Okay, it's going to come up on the AP test at least once, and recognizing this can really help you out. Okay, let's see, other energy stuff. U is the symbol for potential energy. W is the symbol for work or change in energy. Let's see, P is this, capital P is the symbol for power, not to be confused with lowercase p for momentum. Okay, K is used for kinetic energy. E is used for energy. And then the other thing, so this is rotational kinetic energy, if you see anything related to rotation. Okay, then the other energy piece comes in right here if you're talking about gravitation, and this is the potential energy of an object that you're looking at on like a planetary scale as opposed to just like a near Earth scale. So these are kind of our energy equations, and now I'm going to go ahead and put them to use for you in an example here. Okay, so here we have a problem in which we're looking at this graph, and it's a potential energy graph that shows this potential energy with respect to position r away relative to r naught. So we're going to call this kind of position down here r naught. And this position right here is special because it's an equilibrium position. This is where it has the lowest energy level, and so this is where the particle wants to be when this is like the easiest place for the particle to be. Think about, really, I think the easiest way to think about this is like a hill or a roller coaster. If you're in a car, it's going to maybe go up and then come back down, eventually come to rest at this little spot right here. Okay, and so this is the function for that graph. So let me write it out in a way that we can understand a little bit better. A times r over b plus b over r. Okay, and it says a and b are constants, and r is the distance from the origin. Okay, and so it says, in terms of a and b, determine the following. So the first is the position r naught at which the potential energy is a minimum. Okay, so hopefully you're thinking calculus here and you see the word minimum, because if we take du dr instead of equal to 0, so du dr would be Okay, so to get started, I'm actually going to distribute the a. So we have AR over B plus AB over R, and we're going to take the derivative. So for this term, the derivative of R is just 1, so this becomes A over B. And then for this term right here, this is going to become negative AB over R squared. And the way we get that is that can rewrite that as AB R to the negative first. We multiply it by the negative 1 and subtract 1 from it. We get this. We'll set it equal to 0. Okay, add this to the other side. So AB over R squared equals A over B. To solve for R squared, I'm going to multiply that up to there and this B over to there. So AB squared equals AR squared. Divide A over, and we get that R is equal to plus or minus B. Since it's a constant, we'll just say it's equal to B. So now we say, okay, so R naught is equal to B, because R naught is that position where it's at its minimum. Okay, and then it asks us to find what is the value for the minimum potential energy. So we're going to take that equation we found, and we're going to take this initial equation, and we're going to substitute into it for B, for R. Okay, so U of B is equal to A times B over B plus B over B. And that's just 1 plus 1. So that means that that total potential energy there, that minimum potential energy, is equal to 2A. Okay, so then it asks us to, I guess it looks like I cut off part B. Part B was to graph the force. Let me double check that real quick. So yeah, it asks us to sketch a graph of the force. And so we know a couple of things. We know that, as I mentioned before, that U is equal to the negative integral of F with respect to X or R. Okay, which also means that F is equal to negative du dr. Okay, and so we're basically going to sketch the derivative of this. So at R naught, we have a position or a force of 0, because the slope there is 0. And then this is kind of a relatively constant slope, right? Kind of goes constant and stays constant. This is positive, though, so it would be negative down here. So it might go look something like this. Okay, and then before that, we have this slope that starts very negative and gets more and more close to 0. So this is going to start at this point, that means you have a force pushing this way very strong. Here, it's pushing that way just a little bit, and so on. And so it's going to look something like this. Okay, so this would be like our force curve that we sketched. Okay, then it says particles released at R equals R naught over 2. Okay, that's our position. In terms of U naught and M, determine the speed of the particle when it is at R equals R naught. So we know some things. When it's at that position R naught, we said here that the total energy is equal to 2A. Okay, so 2A is going to be equal to U of R over 2, R naught over 2, plus 1/2 mv squared, because whatever's not in this potential energy bucket will be in the kinetic energy bucket. So R naught over 2 is just B over 2. So we're going to evaluate this for B over 2. So let's take this right here and evaluate that. So A times B over 2 over B plus B over B over 2. Okay. This becomes A. So this part right here, the B's will cancel out. And 1/2 over 1 is just 1/2. B's cancel out here, and then the 1 over 1/2 is 2. So this is 2.5 times A. It's not going to work out for us. Okay, sorry. I I messed up the equation. What we're saying is this. We have the total energy, this much total energy, at that point, because this is where it's released from. So it's released from right here, which means it has about this much energy, which means it can kind of oscillate back and forth between here and here. And we just found by substituting B over 2 what this energy level is. And so the total energy of this particle here is 2.5 A. Okay? Then it asks about the speed at R naught, which means that we want to know the speed when the potential energy is equal to 2A, because that's the energy that we had at that position. So if the total energy that we found after being released at this point is 2.5A, that means that when we get to this point, there's about a half joule of free energy to be kinetic energy, because some of that potential energy we had here transformed into kinetic energy as we kind of rolled down this hill. Okay, so we have 2A of potential energy there, and the rest is kinetic energy. So subtract that over 0.5A equals 1/2 mv squared. We'll multiply 2, divide by m, and get that v is equal to the square root of A over m. Okay, then it says write the equation or equations that could be used to determine where, if ever, the particle will again come to rest. It is not necessary to solve for this position. Okay, so energy is equal to potential energy plus kinetic energy. So we know that we gave this particle a total of 2.5 joules. And we're asking now to find when it's going to come to rest, which means that at that position that K is equal to 0. We want to solve for R, so for A we would substitute in this equation right here. And so that our equation to find out when it's going to come to rest would be that the total energy 2.5 is equal to our equation for potential energy. Okay? And so this would be the answer to part D here. And then it says to briefly describe the motion of the particle over a long period of time. Well, as I said, it's going to kind of oscillate back and forth because it has enough energy to go up to here, but it can't get away. So like if you had like something stuck between two hills and there was no friction to slow it down, it kind of just go back and forth until something took that energy away. So it's going to kind of roll back and forth, back and forth, back and forth. Okay? Please let me know if you have any additional questions about energy. You can email the questions or school questions and I'll get back to you on them.